Hello folks, welcome back. So it's another data analysis video, and in this video what I'm going to do is demonstrate how to conduct a robust independent groups ANOVA. The last few videos have focused on repeat measures designs, but I'm going back to an independent groups or between subjects design where our participants only contribute scores in one of the groups of our categorical independent variable. Okay, and in this case, what I'm going to do is I've demonstrated previously how to conduct an independent groups ANOVA, but here we'll conduct an independent groups ANOVA and we'll find that the data violates the assumption of homogeneity of variance with a Levene's test. So we need to do some sort of adjustment for the ANOVA to account for this. So we need a strict and more robust ANOVA test that doesn't make the assumption that the groups have equal error variances. Okay, so the data set that I'm going to use contains responses of it's a data set that may have been collected by one of my colleagues. It may have come from a textbook somewhere, but it gets used frequently for teaching purposes, and it contains the responses of 152 police officers to some sort of large questionnaire study investigating the topic of stress in the police force. And what I'm going to do is conduct a one-way robust ANOVA on an independent variable of length of service. This independent variable length of service, it records an officer's length of service has been transformed into a categorical variable by binning length of service into three groups. So group 1 includes any participant who had up to 10 years service in the police. Group 2, any participant who had from 10 to 20 years service in the police, and Group 3, any participant who had over 20 years service in the police. And the dependent variable is a Likert scale variable that records the participants' mean scores on a 7-item 5-point, so 0 to 4 Likert scale questionnaire measuring something called operational uplifts. And this operational uplifts was a measure of a series of operational factors and whether they were rated positively or negatively by those officers over the previous months or the previous month of their service before the questionnaire was conducted. So what I'm going to do here is conduct a Levene's test for homogeneity of variance. We'll find we get a significant Levene's test, so we can't assume equal variances. And then I'll conduct a robust ANOVA, and that will be a Welch's ANOVA test. That's a test that allows us to do an ANOVA and where equal variances can't be assumed. Okay, and then if that's significant, I'll follow that up with a robust post-hoc test, and the one I'll use is the Games-Howell pairwise comparisons. Okay, so I'm going to use a number of software libraries in this analysis. So I'm going to import pandas as PD, from scipy.stats I'm going to import Levene. So I'm going to use scipy to conduct the Levene's test. I'm going to import NumPy as NP, as is the convention, and I'm going to import Penguin as PG as well. So a couple of the methods we use are from Penguin Software Library, which is a great software library for conducting these types of classical frequentist statistical analyses. So the data set I'm going to import, I'm going to call it uplifts because that's kind of the name I've got it saved as on my laptop as a CSV file. I'm going to import it using the pandas read CSV method, and let's print out the first kind of 5 lines. And you can see we've got a number of variables: whether the participant has children, their sex, these are all kind of numerically coded, service group 1, 2, and 3. So remember, 1 was up to 10 years, 2 was 10 to 20 years, 3 was more than 20 years, the age of the participant. And then we've got a couple of other things here measured on a scale. One of them's upper UPM. That's our operational uplifts measure, our DV. So service groups are IV, upper UPMs are DV, and it returns some sort of floating point measure. And we've got org UPM as well. That's a final variable here. That's organizational uplifts. We're not going to bother with that. The two we're interested in here are service group and operational uplifts for this particular analysis. So let's start by conducting the Levene's test to check the assumption of equal variances for the 3 length of service categories. So firstly, what I need to do is create 3 new objects, 1 for each length of service category. and then I'm going to pass these to the SciPy Levene method to check for equality of variance. So all I'm going to do really is create 3 objects and use them as the arguments for the SciPy Levene method. So I'm going to use the series.map function from pandas to add labels to the service group categorical variable. Okay, so I'm going to create two objects that consist of lists. Object A is the numbers 1, 2, and 3. Those are the numbers for our service groups. And I'm going to, object B is a list containing labels. And we're going to basically just zip these, use the map method and zip these together. So 1 gets the label up to 10 for up to 10 years, 2 gets 10 to 20 for 10 to 20 years, and 3 gets 20 plus. So all I'm going to do here is take our uplifts data frame, append a new variable to it called service categories, and that's going to basically take the uplift service group variable, and it's going to map these labels everywhere it finds a 1, a 2, or a 3. Okay, and I'm going to use this a dictionary, and it's telling it to zip A and B together. So if I run that, you should see we've now got this new variable appended to the end. That's so where we have a 1 for service group, it should say up to 10 years. Where we have a 2, 10 to 20. Where we have a 3, 20 plus. Okay, if that's worked correctly. Okay, then from that, what I'm going to do is create a couple of new objects. One base called cat for category, which uses this service cat object, and one called scale, which takes our operational uplifts scale variable. So cat's obviously our IV, scale is obviously our DV for an ANOVA type model. And then I'm going to create 3 Boolean objects that basically split our cat object up based on the 3 groups. So cat 1 is going to be up to 10 years, cat 2 is going to be 10 to 20, cat 3 is going to be 20 plus. So I've demonstrated this. I've done similar things in previous videos, and it's all just manipulating data so we can use other objects, extract data, save them as objects, and use them as parameters arguments in the different methods or functions. So finally, what I'm going to do is create these new objects, which basically take our cat1 object and map it to our scale. So it's going to, if what we're effectively doing is getting a bit more granular. We're taking all the cat1 scale operational uplift measures and saving them as one object. Same for cat2 and cat3. So if I run that, and then we can use this, we can run this Levene's test using the Levene method from SciPy. So I'm going to call Levene. So remember above here, when I imported it directly as Levene from SciPy.stats. If I just from SciPy import stats, what I would have to do to call the Levene method would be stats.levene, and then all these parameters, all these arguments. And all I'm doing here, you can see, is I'm passing the 3 groups that we want to compare using Levene's test. That's this object, categorical operations, up to 10 years, operational uplifts, categorical variable, operational uplifts 10 to 20, and then the third one, and I'm asking it to use the mean as the measure of center. And what we see is we get a Levene's test statistic of 4.68 and a p-value of 0.01, so a statistically significant Levene's test. So what this means is we can't assume homogeneity variance for this particular data set that we've got here. So as a consequence, we need to conduct a robust ANOVA test that doesn't rely on the assumption of equal variances between groups, and a test that adjusts to allow for the fact that our data violates that assumption. Okay, but to report the above Levene's test, it's basically an ANOVA. We would also need the degrees of freedom. When you use the kind of SciPy Levene method, it doesn't give you the degrees of freedom, but when you report any kind of F value, or a Levene's test is based on an F distribution, we'd report also the between and within groups degrees of freedom, and we'd have to calculate them manually here. So to calculate the between groups degrees of freedom, that's k minus 1. The within groups degrees of freedom is an n minus k, and the total degrees of freedom, we don't really need that, but we can calculate it whilst we're here as n minus 1. And k is the number of categories or groups we have, n is the total number of scores or the total number of observations or participants we have. And from this data set, then what that means, this data set, I haven't kind of obtained the info anywhere, I haven't kind of asked Python for that, but it consists of 152 participants, and we've got 3 groups for the independent variable. So that was up to 10, 10 to 20, 20 plus. So the between groups degrees of freedom is 3 minus 1. So we've got 3 groups minus 1. So the first between groups degrees of freedom is 2, and the within groups is n minus k. So 152 is our n, our sample size, minus k, the number of groups. That's 152 minus 3, or 149. So what we would do here is report the results of this Levene's test as follows. It's an f value, so we've got f, open parentheses, then report our between and within groups degrees of freedom. So say the f statistic is 4.68, p is equal to 0.01 if we round that to 2 decimal places. So that's how we'd form the report that if we were going to. So we've got a significant Levene's test. We can't assume equal variances, so we're going to need to conduct a robust ANOVA test. And what we're going to do here is use Welch's ANOVA. And to do that, I'm going to use the Welch _ ANOVA method from the Penguin software library. So it's a robust ANOVA, it's suitable for independent groups designs, and when we use the Penguin method, it takes the parameters for the data, the DV, and the between subjects factor. And you can see that there, so you can see the call I'm using pg.welch _ ANOVA, so penguin.welch _ ANOVA. I'm specifying the data we want to use is our uplifts data frame, the dependent variable is our operational uplifts, and the between subjects factor is our service, our cat service _ cat, so those categorical service labels that we appended. Let's run that. And what we see here is we've got an f value of 4.63 and a p-value of 0.01. So the above analysis showed a significant result, indicating there is a significant difference between the 3 length of service groups in terms of their mean scores on that operational uplifts DV. So to report this, we'd probably state something like Welch's F, and then open parentheses, report our degrees of freedom, which are 2 and 83 in this case, and then that's equal to our f value 4.63, comma p is equal to 0.01 if we round that to 2 decimal places. So note here that the second degrees of freedom are 83. So the within groups degrees of freedom has been reduced to 83 for this test. And this is how the Welch's test adjusts the p-value to make the test more robust. So it's like the test is being conducted on a smaller sized data sample, so making the test stricter and less likely to produce a significant result when one does not exist. So we've got, what we're finding here is, using Welch's ANOVA, we've got a significant f value, we've got a significant ANOVA model, so we can now follow this significant result up with some post-hoc tests. And an appropriate post-hoc test, as we can't assume equal variances due to the significant Levene's test, would be a Games-Howell test. Okay, so before we conduct the Games-Howell test for these post-hoc comparisons, it's kind of useful to get a printout of the mean scores for the 3 groups. So if we have these available or to hand, it helps with the interpretation of the results. So that's all I'm going to do here. That's all I'm doing in this cell here, is I'm using some print statements. I'm using some f strings, which allows me to kind of, within a string, sort of embed some type of object, which is within these curly brackets. And all I'm doing is I'm taking each of our 3 groups, those objects we created up there when we did the Levene test, I'm taking each of these objects which have the kind of mean operational uplift scores for each group. And I'm basically just asking it to print out the mean. I'm using this dot mean and round to 2 decimal places. So if I run that, you can see, so the mean operational uplift score for people with up to 10 years service is 3.05. For 10 to 20 years service, it's 2.93. For 20 plus years service, it's 2.64. So lowest for the longest serving officers. Okay, so this is just to help us eyeball it quickly. Let's conduct the Games-Howell pairwise comparisons. So previously I've demonstrated how to use pairwise tests to run pairwise t-tests using Penguin. So the Penguin method for these kind of robust Games-Howell pairwise comparisons is it's kind of really similar syntax. It's pg.pairwise_Games-Howell. Okay, and then in parentheses you specify pretty much the same arguments as you would for kind of the pairwise tests method. You say what the data is our uplifts data frame, the DV is our operational uplifts variable, the between subjects, the independent groups grouping variable is our service cat variable, and I'm asking for a hedges effect size. Okay, so if I run that, you can see it's done these Games-Howell adjusted pairwise comparisons. Okay, so robust pairwise comparisons. And in a similar way to the Welch's ANOVA, it probably adjusts the degrees of freedom to make the test a little bit more robust. So we're seeing when we compare 10 to 20 years to 20 plus years service, we get a t-value of 2.06 and p is 0.10. So not a significant difference there between 10 and 20 and 20 plus. When we compare 10 to 20 with up to 10, we get a t-value of negative 1.15 if we round that to 2. So you can ignore the negative sign essentially and just report the absolute value of a t statistic. And the fact whether it's negative or positive is just a function of which mean has been subtracted from which other group mean. Okay, and in this case, the larger mean has been subtracted from the smaller mean. You can see that 2.93 minus 3.05 is what this would be. And a p-value of 0.49, so again not statistically significant difference. 20 plus to up to 10 years, so the longest serving with the least service, we get a t-value of negative 3.05, so t-value of 3.05 and a p-value of 0.009, so we get a statistically significant difference. So what we do here, the above comparisons indicate there's a significant difference between 20 plus service group in terms of operational uplift scores and those with least service, the up to 10 years service group. However, all the other comparisons are non-significant. So we'd report these results as I've kind of done here if we report it formally. They're t-tests. So we'd state, you know, the up to 10 versus the 10 to 20 years, t, and then brackets, degrees of freedom, in this case is 107. T, the actual test statistic is 1.15. If we round that, p equals 0.49. So no significant difference between the groups in terms of mean uplift scores. And we can report their means there just so you can look at them and say, oh yeah, it seems to make sense. 3.05, 2.93. They're quite close, they're not significantly different. The only one that is this third one. We've got t, degrees of freedom of 57, the t-value is 3.05, p equals 0.009, and we can see here that up to 10 years had a mean of 3.05, 20 plus years had a mean of 2.64, and those are statistically significantly different, with the up to 10 years having a higher mean uplift score. Okay, so that is how to conduct independent groups ANOVA in using different software libraries where you conduct a Levene's test, you find that you get a significant result, so you can't assume equal variances and you need a more robust ANOVA test. So a useful one to use is the Welch's ANOVA, and you can use Penguin to do that. And then if that's significant, to conduct post-hoc tests, you want a robust post-hoc test such as Games-Howell, and you can use the penguin.pairwise Games-Howell method for that. Right, okay, that's enough of that. I think from now, the next few videos, we're going to move on to factorial and mixed designs. So this is a lot of videos about ANOVA, but it's probably worth the repetition and covering all sorts of different designs, because it's a very commonly used approach to analysing data for a lot of experimental designs in psychology and behavioural sciences. Okay, thank you for listening. I hope it was helpful.